Welcome to the fifth talk of Human Factors in Design. I'm Joseph Giacomin, and today we'll be discussing a very important topic in Human Factors and Ergonomics, which is the question of movement or human motion. Movement is fundamental property, quite often overlooked, not often given all the attention it deserves. If you look at any scientific definition of the word life, meaning anything that's alive, usually there's a relatively long list of parameters or concepts which are used to judge whether something's alive, such as an insect, or something's not alive, such as a rock. One of those parameters, or one of those criteria, which normally emerges or normally is found in these lists of criteria, is that of movement or motion. Something that has no ability to react to its environment, react to stresses or things acting upon it by motion, something that can't move any part of itself in any way to react to its environment, usually is not alive. So movement is essential to life, actually, and it's one consideration amongst the many human factors and ergonomics. It's very important, but oftentimes it's not given the priority it deserves. So, for today's discussion, we'll start with the 1950s. As I've said previously, the fields of ergonomics and human factors dramatically accelerated knowledge and developments in research during the Second World War, and as we've said before, it's because the machines of the time had begun to exceed or go beyond human abilities, and many times the success or failure of the aircraft or the tank or the submarine or the radar system was very much due to what the human, what the operator, what the pilot could achieve. Now, that vast acceleration in the research and the knowledge continued into the post-war or Cold War era. And in the 1950s, early 1950s, there was a vast series of experiments and tests and studies performed at the Wright Field, what's later was called Wright-Patterson Air Force Base. A large number of studies were done by a team under the guidance of Paul Fitts of the US Air Force, and due to the many things they demonstrated, the many things they found, the many proposals they made for modeling human motion, a lot of the equations and the things we use when we talk about human motions are referred to as Fitts' law, or Fitts' paradigm, or Fitts' model, or Fitts' data. So Paul Fitts is seen as if not the founder or the originator of all study of human motion, certainly one of the founding fathers and one of the key or significant individuals in the field. So early 1950s. What kinds of things did they do, and what has remained with us today? Well, a vast number of experiments at Wright-Patterson Air Force Base were performed with a very simple type of test, a very simple paradigm, and it's what's referred to as the Fitts paradigm. And it's as simple can be. Something like two sheets of paper placed a certain distance A, as in the diagram A, apart one from the other. Each one of them is wide an amount W, and we put these two sheets of paper on the desk or on the table. We bring some participants, some colleagues in to do the test. We give them some sort of a stylus or a pencil or something to hold and to tap between the two. And the Fitts paradigm was basically this simple test. At the fixed distance A, for the fixed size W, take the stylus and tap between the centers if you can target and hit the centers. tap between the centers of the two sheets of paper, which are sitting on the desk, for 20 seconds, and the person running the test would be there with a stopwatch, and when he gets to 20 seconds or she gets to 20 seconds would say, stop, that's the end of the test. They would count how many actual taps on one or the other of the sheets of paper actually occurred. So you go really fast, and we count how many taps actually occurred, and that was the FITS paradigm. The idea being we can investigate the effect of distance between points you're trying to reach. So imagine buttons on the dashboard of the car, on the heater control of the car, on imagine keys on the keyboard that you're trying to reach different keys. We can study how far apart A, that number, could be and what effect that had on the ability to actually hit it, on the speed I could move. And we could look also at the effect of the width of the target, because common sense says that if I try to reach a button and the button's quite big, I should not have great difficulties reaching it, and maybe I can do it really quick because it's not going to be a problem if I hit one side of it or the other or the center. I don't have to spend any time trying to target because it's really big and I will hit it easily. Instead, if it's really tiny, the button, I might have to dedicate some effort to guiding my hand to make sure I don't miss it, and that's all time I'm losing from the motion that's being measured in the FITS paradigm. So looking at human motion and what kinds of things would slow you down, the size of the target, how far away you have to reach to get it, and so forth. That was the nature of a large number of tests. Not all they did, but it's a large number of tests that Paul Fitz's group did at Wright-Patterson Air Force Base. And lo and behold, doing hundreds of tests with dozens and dozens of staff members of the Air Force Base with different distances or different sizes of targets, looking at the data and plotting the data, how much time against each of the parameters, over and over again, the data sets from the different tests seem to fit a pattern. And that's what's nice about mathematics. That's why we use mathematics in fields such as engineering. If we can find an equation, meaning a set of numbers and parameters which capture the pattern, we've got a model. We've got a simple way not just to explain it and to define it, but we've got a simple way to make predictions by changing some of the numbers and see what changes with the final result. And lo and behold, Fitz's team found that there was indeed one mathematical equation amongst the many they tried which fit the data sets incredibly well. And the equation is what's being shown here on this slide. And this equation has come to be known over the years since the time of the original studies. It's been given the name Fitz's law. Now, I draw your attention to the word law because in ergonomics and human factors, we don't have that many laws. In many fields of science and chemistry and engineering, there's a vast number of laws where there's only one equation or one explanation for some chemical reaction or some calculation of forces and motions. Newton's law being familiar to everyone. Okay, in science there's lots of laws, but with people, which are biological systems, each of which is slightly different due to small genetic variations, people's behavior is very complex and doesn't fit that easily into too many laws. So I draw attention to the word law to say, if this particular equation captures this wide range of data sets to the point that it can be called a law with some degree of confidence, that's a very powerful result. It's something we're not going to escape from very easily. It's something that probably will find use and be very useful for design purposes. So I draw attention to the wording because words are very important. The way we express ourselves, the words we choose for things are incredibly powerful. This one happens to be a law. And what is the law Mr. Fitz and his team devised? Movement time, mt, is equal to, is calculated from, can be determined from an equation consisting of A, which is just a number, a constant value, which is related to the nature of the experiment you did, and we'll talk about it in a moment. B, another constant value, just a number, 3, 4, 6 is just a number, it doesn't have any special meaning. It's related to the contextual constraints of the experiment as well. Log base 2 of 2 times the quantity A divided by the quantity W. So 2 times how far apart, measured probably in meters, the targets were, divided by how wide the targets were, W. And just like the word law, I would draw your attention to the logarithm. The logarithm in this case is a base 2. This is not the base 10, which we use much more frequently in science, the one which is useful in terms of capturing things that vary over orders of magnitude. Something that can take on the values 1, 10, 1,000, 10,000, 100,000, a million, a billion, that usually kind of situation you tend to use a logarithm with the base value 10, because that would be a very convenient manner to talk about that kind of numbers. Instead, this is base 2. Those of you who come from an information systems or computer science background, this may look suspicious because base 2 is what you use when the options are 0 or 1, which is exactly what a digital computer does. So this is a digital base logarithm between the choices of there is the signal or there isn't the signal. And it's very odd that this should show up in something about moving your arm and measuring the seconds. Where did this come from? Well, the interesting part is if we plot a little diagram, X and Y, and on the diagram we put along the x-axis this logarithm base 2 of those things inside. Put in the A, put in the W, calculate the logarithm base 2, and we plot against that on the y-axis the movement time. In the case of Fitz data, this is usually in seconds, measured with the clock. If we plot that, we get a pretty good approximation. Looks a lot like a straight line. Therefore, this thing of what's inside the logarithm and the logarithm to the base 2 is capturing something fundamental about how long it's taking to do the motion. And what Fitz and his team suggested is, if we look in maths and physics, and we look where logarithms with a base 2 tend to appear and what they tend to be used for, functions or formulas of logarithm base 2 of some number you're using, some value of n, they tend to be in all those equations and all those laws and all those measurements, which are about information, like with the digital computer. It's usually used to capture, to express how many bits, zeros or ones of the computer, are needed to separate between n possible options. So if I had 10 buttons to push, it's how many zeros or ones I need to give one representation to each of the buttons we're going to push. So this logarithm base 2 is an information-based metric, just of the type we use with computers and digital systems. And what Fitz suggested was that this term log base 2 of 2a over w is capturing what's happening with people, because what's limiting the person's ability to get from one point to another is not how big the muscle is in the arm or the leg or the hand or the foot. It's not how strong you are and thus how fast you can move physically. It's how much time it takes your brain to see where your hand is going, send the information to the brain, calculate where you have to move next with your next phase of motion, send a signal back to all the different muscles that need to be synchronized together, and then continue on with the movement towards the target. So what Fitz and the team have proposed, and in many ways have been confirmed from neurological measurements and physiological measurements on actual neurons of the nervous system, over the years has been somewhat accepted that this model, this maths equation works, and it has this structure to it, because what's slowing me down is not how big I am or how small I am or how heavy my arm is. It's how long it takes me to see where I'm going, control my hand, make any adjustments when I'm going the wrong way, and continue on until I actually hit the target. It's an information processing limitation. It's basically a recognition that, like computers, we have a maximum speed that we can see, hear, smell, touch, taste things, think about it, and then do something about it. This loop, action and reaction, has a fixed IT or information-based limitation. There's only so many bits per second or so many bits per minute that we can do in terms of maximum speed, and Fitt's law is capturing that for the situation of looking how fast you move your hand or your foot. So in Fitt's law, as we said, movement time in seconds is given by this expression. The variables that we have interest as human factors people are how far away the thing is, A, and how big the button or the handle is, W. But the A and B are needed to fit an equation to a specific data set. So the question is, what are the A and the B? The value of A just simply gives the y-intercept where you cross the y-axis on the diagram. And it's basically a measure of how you did the experiment. Different experiments with different shapes of targets or different heights of tables or different situations, restraints on the person or not restraints, they might move a little bit the A one way or the other. It's not really the most interesting part of the expression, but it's there and it's needed. The other question is, I wonder what the B might mean. The B is the slope of the line, and it's determined in large part, in large degree, by which body part we're talking about, how big it is, how big the muscles are, how fit the person is. It's really about what I said the Fitt's law in general is not completely about. This little part of the equation is trying to capture the effect of a person who's very athletic and very well trained, maybe can move just slightly faster. A person who's less athletic or who's less healthy or smaller or something might be just slightly slower in the motion. So we have a y-intercept, which is a basic starting point for the data set, and we have a b constant, another number, is just a fixed number, which captures something about how big or small, how easy or difficult it is to move that part of the body. This particular diagram is showing for different body parts. We have the finger F, we have the wrist W, we have the arm itself A, we have tests in which the tapping is being done with the finger or the wrist or moving the whole arm back and forth. And you can see that the smaller part of the smaller body part, which is the finger in this case, by being small and light and having very strong muscles to pull it, that can move a little bit faster in seconds, and the other curves are above it, meaning more seconds to complete the task, more seconds to do the movement. So the equation has a structure based on a log base 2. It's telling us something about information going on in the brain, and the nervous system is very strongly involved. We have a constant A, which is the starting point of the y-intercept, which is just a fixed value that the data set would be shift that much. It changes a little bit from one kind of test to another. And then we have this value of B, which is telling us something about, you know something? The B is probably going to be different depending on which body part we're talking about. So that's Fitts' law. And over the years, Fitts' law has been attempted, tests have been done for a wide, impressive range of movement applications. We've had people tapping things with their foot. We've had actuating different controls with your leg or your arm or your elbow. We've had all kinds of tests in which people have interacted with all kinds of machines and instruments, and people have been sitting there with the stopwatch measuring the amount of time to complete a certain number, how many actuations occurred in a fixed amount of time. So Fitts' law has proven to be an equation that works for a very wide range of situations and to be fairly accurate in those applications. Now, what kinds of general philosophical design things, what implications, what lessons can we learn from this equation and take home with us to consider when we're designing things? Well, the biggest one, the most important one, which everyone in design tends to remember, even if they don't recall the details of the equation, even if they don't know the full background of the story, one thing people do tend to notice the first time they encounter the issue and tend to remember it is the question of the speed accuracy trade-off. An important implication of Fitts' law is the so-called speed accuracy trade-off. Since the rate of information processing is constant, movement patterns can be characterized either as fast, high speed, or accurate, carefully done, on target, but not both at the same time. And the little slide I have here is suggesting we have sports which are based on speed and velocity. Those sports, yes, you can run very fast, but you do tend to drift a little bit back and forth from your lane. You have other activities, human activities. Imagine the dentist, imagine the doctor, the surgeon in the hospital. You have activities where precision, high precision, is the key parameter. And you'll have seen this a million times in a million ways when a dentist is operating, a surgeon's operating, when someone's making a watch, a mechanical watch under a magnifying glass, the motions will tend to be slow so as to ensure accuracy of motion. So we have, as designers, to consider, particularly human factors and ergonomics experts, we have to be very conscious of the fact that when we design certain activities and certain interfaces and machines, we cannot demand both of these properties simultaneously from the poor person who's sitting there operating the device. We must not put the person in a difficulty by demanding both simultaneously. Now, typical applications were things like motion time, which might be estimated by the designer very quickly with a hand calculation using Fitts' law. The type of situations where these things come very much into play, things like driving a road vehicle, stopping at a junction or a red light. This is a typical situation where the light might flip red or you might spot the stop sign. And then the question becomes, how long will it take you after you've seen it to control your foot to push onto the brake pedal and probably the clutch and bring the vehicle to a stop? Questions of reaction time, which is a form of motion. The motion part of the reaction time is a big element of it. These are very important questions. Now, one study which I often cite, which is a rather old one, is the 1986 study by Morrison, Swope, and Halcombe, and they were looking at reducing reaction times, and they asked a very simple, practical question. Fitts' law tells me that the A and the W will change the movement time mt. Well, let me try modifying the A or the W or some other things related to them in one plane or the other plane of the pedal, and see if in a driving simulator we do see the kinds of differences we would have expected from the Fitts law. In this case, what they did was they put a brake pedal and an accelerator pedal on the driving simulator, and these pedals were varied in size. They were varied in the distance apart, so you can see here in the diagram the value of C. We had tests where the brake pedal was close to the accelerator pedal of the car, other tests where it was further away or further away still. And they tried looking at Fitts' law in both planes or both directions. So we moved them apart side to side, but we also moved them apart in terms of the depth. If you look at cars today, the accelerator pedal and the brake pedal are not in the same plane. One is a little bit deeper into the car than the other. So they tried, well, let's put one pedal, let's put the brake pedal on the same level as the accelerator, below the accelerator or above the accelerator, such that the foot is going down further or less. Let's see if that has an effect on the movement time. And the test was just a simple test where they light something up and you just have to push the pedal to stop. What did they find? The data is here in the table. I wouldn't worry too much about the numbers. They're not particularly fundamentally on their own right. But what is important is the general conclusion. Reduced lateral separation between the brake and the accelerator was sometimes found to reduce the movement time to get from one to the other after seeing you had to stop. But the difference was rather small, and in this particular set of tests by this particular group of researchers, it was not found to be statistically significant. The numbers came out different, but the differences were so small that you wouldn't be confident about it in a statistical sense. On the other hand, changing the depth of the pedal into the floor of the car did make a statistically significant difference. Still smallish numbers, but big enough to be confident there is a difference and there's something happening. Reducing the brake pedal depth to the same value as that of the accelerator pedal or to less produced a statistically significant reduction in time. So if I move the brake pedal from where the average car would have it, if I move it a little in this sense, in this direction, I can move my foot faster. I'll be able to stop the car sooner, and that means stopping before, a little bit earlier, before I get to the junction. Now, the data that these researchers did in their experiment, in their simulator, the difference when you move the pedal was 0.01 seconds. Small amount, but in a vehicle moving at motorway type speeds, 88 kilometers per hour, at that kind of a speed value, that's roughly 2.5 meters. That's not negligible. So what these researchers found was that yes, the Fitts law does seem to be confirmed, and in practice, the kinds of changes that seem reasonable to make to car pedals, when you look side to side, you really can't move it enough to make a huge difference. They can't be one against the other exactly the same, or you might get your foot on both at the same time. But in the other sense, in the depth or the plane of the pedal, there was enough of an improvement to save 2.5 meters. That might save somebody's life at a crosswalk if we're trying to come to a stop. So why is it that all of the cars in the parking lot out here, why is it that none of these cars would have the brake pedal and the accelerator pedal on the same plane, or the brake pedal below the accelerator pedal, as the data from these researchers in the 1980s would seem to suggest could bring benefit. Why do no cars really do that? This is an interesting point which we raise here, because even though not strictly related to the question of motion, this is a typical example of the complexities of the life of any designer. In design, we're trying to take always an infinity of complex considerations and narrow them down to as few as possible to permit us to get on with the task of designing. Designers have the unenviable task of having to reduce an infinity of complexity in the real world down to as few things, as few numbers and parameters as possible to carry on with the design process. In this case, what's happened here is that the speed with which you move your foot from one pedal to another, it's true those researchers saw you could do it better, but that's not the only thing involved. And a designer has to be careful of all the other things which may come into play. And in this case of movement time, there's a problem that if you put the two pedals on the same plane, or if you put the brake pedal below the level of the accelerator, what you find very quickly when you do tests like that in a driving simulator is that people get confused about which one they're putting their foot on, or put it on both at the same time. And this kind of thing is very dangerous from a safety point of view. There's more to human factors in ergonomics than just movement time. Good to know, a check that needs to be done, but in many cases that might not even be the dominant or fundamental design criteria. For example, 1980s, perhaps very few of you will remember this vehicle, but the Audi 5000 automatic came out in the United States of America in the early 80s. This vehicle had the brake pedal and the accelerator rather close together, and a bit too close together, very similar to some of these parameters that were tested in the research study we just discussed. What happened with this vehicle? Too many times the drivers would push the wrong one, because it was they were almost on the same plane, so you wouldn't be confident when you reach it which one it is, because they're too close together. And in the case of the Audi, a number of people were killed. People were getting out of their car or just beginning to start the car. The door might have still been open. They pushed the wrong pedal, the thing lurched forward, and they got dragged under the car. Or they hit somebody in the driveway of their home, thinking they're braking, but instead they were accelerating. The Audi 5000 had a lot of these accidents. I think I recall as many as perhaps 15 or 20 people getting killed while using this vehicle. It created quite a financial crisis for the company. So this is just an example of the fact that many times one single design parameter may seem really important and useful and helpful, but the thing is, a designer has to be very careful to check all of them, put them in order of priority, and make sure that all the main design requirements are met. This is an example where movement time was as helpful as it is and as important as it is. It wasn't the only, and in this scenario wasn't the main issue that needed consideration. Another aspect of movement, whereas Mr. Fitz and a whole generation of researchers gave us a vast amount of information relative to how fast or slow, how accurate or inaccurate, in more recent times there's been at least 20, 30 years of research into motion comfort. How comfortable is the motion? Any movement a human being does involves doing something, actuating something, turning the button on, turning the steering wheel, whatever it is. But there's also the associated question of not just how successful or how fast you were at the task, but how comfortable and happy were you along the way. And movement comfort is a big issue. It's a big issue in particular with respect to vehicles. And road vehicles like automobiles movement comfort is a big issue. For example, in this slide is illustrated the sequence of getting into the car, the ingress into the vehicle, and when you come back out, it's called the egress. Ingress and egress into vehicles of any type. In many cases, ingress and egress also in buildings, in various rooms, in various parts of the structure, in various facilities. These are big issues where comfort comes into play, because you'll be doing it many times each day, and if you have to bend a lot and use a lot of muscle force or assume a very awkward position, it can be uncomfortable. Some work I myself did now more than 20 years ago with automobiles. We had a driving buck, or a driving simulation, where we had a mechanical frame to represent the door frame of the rear door of one of our automobiles at the car company. This particular door frame could be lifted, the roof line up or down. The sill, or the point that you have to get your leg and foot over, could be lifted up and down. The seats could be moved up and down, back and forth. A whole set of geometric parameters could be physically modified. They were bars with joints that could be reconfigured into different positions. And then we could ask people to get in and out from through this door frame, this little ring, this little frame that was not a real car. It was just representing roughly the geometry of the rear frame of the rear door. We would get people in and out and measure various things to see which configurations, which geometric positions seem to be more comfortable. Now, what kinds of things do human factors and ergonomics experts measure? It can be any number of things, some of which can be incredibly practical. For example, here on the table up on the left, we have all these different configurations, so you can see all the variations we did. What did we measure for them? Here in this table 4 is one of the most useful, one of the most helpful of the things we measured, which is also one of the most trivial. We asked the people, after getting in and out about 10 or 15 times, we asked them which parts of this door frame, and you can see from the picture on the right what it looked like, which parts of these frame, or which parts of the door itself, which corners of the door, do you feel were obstacles to your getting in or to your getting out? We asked separate questions, one set for getting in, one set for getting out. Which parts were obstacles, were inconvenient? Which parts hindered you or made the motion uncomfortable? And just looking at the number of citations, you can see how low you put the roof of the car, which means how much you have to bend your neck to one side to get under it when you get into the car. This was by far the biggest issue. So those sporty vehicles, those sports cars with very low roof lines to reduce aerodynamic drag on the vehicle, but by having a low roof, when you get in, you have to do a lot of bending of your neck and back. Incredibly uncomfortable, and lots of people would complain. Lots of customers would end up complaining they didn't feel it was very nice getting in and out of their car. Other parts that interfered or created discomfort for the people, the door itself, the door edge, the wheel arch, and so forth and so on. Another one of the very basic, simple, trivial type things that was asked, but is incredibly helpful from a human factors ergonomics perspective in terms of putting some numbers on these issues that are being created for people from a comfort point of view, was how many times did the thing actually block you or slow you down or stop you from getting in? And again, how many times did you cite that part of your body as being uncomfortable when the parts of the vehicle were blocking you or hindering you getting in? So particularly for those configurations which were a little bit tricky and uncomfortable to get into, where was the source of discomfort on your body that you're using to give your judgment about the problems created by that part of the vehicle? Most of the time, the head and neck, having to bend to get in under the roof, or having to bend around the corner of the door itself. Those kinds of things immediately created some degree of discomfort. Left foot, right foot, because you have to put your foot in, carry your weight until you're lowered onto the seat, and then transfer the other leg in. So the head and neck was the region suffering the most discomfort due to the impediments of those parts of the vehicles. The left and right foot and ankles were often cited by people as being uncomfortable, particularly after a large number of ingresses and egresses. If you ask them to do this 40, 50 times, they might have a sore leg or a sore ankle. So again, very simple measures. One, the previous slide, tell me which part of the vehicle you think is creating you problems and making you change your trajectory. Two, this particular slide, which part of your body hurts after you've done this test many times? Very simple questions, very simple tests, very useful answers. Now, to finish up this section, a couple design classics. The first of the design classics, the Dyson Ball. A well-known vacuum cleaner by the Dyson company, very famous product, often showing up in design museums or design exhibitions. The idea that we could use a very large ball or sphere and a couple of pivots to rotate on it and rotate around it and make the motion of the person who's doing the vacuuming much more pleasant, more comfortable, possibly even faster. This was a great intuition and great observation of the Dyson company. So what's happened here is we've taken motion, how fast and how easily we move the wrist and we move the upper arm and the elbow. We've taken the motion as the starting point for a set of design configurations and revisited the vacuum cleaner design based on this set of considerations. We've redesigned it around the person's wrist, basically. And the Dyson Ball makes the motion easier, getting under things, getting around things. A great example of how motion or movement can be taken as the fundamental criteria to reach in a design, and how transformative and how useful some examples of doing that can be. The other design classic that I've added for today's discussion is the Tolomeo, the desk lamp you see a lot on television, on various movies and TV series these days. A very nice, a very posh, somewhat expensive desk lamp. Now, Tolomeo aesthetically is very pleasing. It's very clean and simple in its lines. And Tolomeo is clearly very effective in terms of the lighting system adopted and the sizing of the artifact and its weight and so forth. So Tolomeo is clearly a very functional device and a very aesthetic device. But what makes it somewhat unique, what makes it quite different from most of the competitor products, at least at the time of its initial launch, today there's many imitators, Tolomeo, the designers, they put a lot of time and effort into considering the motion that the device has to go through and the way it feels and the interaction that occurs to achieve it. So DeLucchi and Fascina, with this lamp, they developed something that turning the light on and off is just touching this little rod that comes down, and a very gentle touch in any direction would turn the light on. But more importantly, if you look at the main joints of the device, if we look here at what could be considered the elbow of the device and look at the base, we can see that with respect to the traditional types of lamps from the Industrial Revolution times that had straight springs, and the spring would resist you directly in proportion to how far you move it. So the resistance would change over the motion due to the change of position. These have, you can see the little cable winding around a pulley at each of the joints. Inside the joint, attached to that pulley, is a nonlinear spring. And what happens is the spring has been designed, the pulley has been sized, the geometry of the arm has been chosen such that moving it up or moving it down produces not just a smooth movement, but the resistance that I feel from the lamp, how much it doesn't want to move, let's put it that way, feels about the same at the start of the movement, in the middle of the movement, and the bottom of the movement just before I finish. Sort of like neutral buoyancy under the sea, if anyone's familiar with neutral buoyancy in diving. So the motion is relatively frictionless, which is incredibly pleasant, and the resistance force is not perfect, but it's rather neutral. Thus I can move it around gently and enjoyably with this feeling that the lamp is following me without resisting it. So again, it's an exceptional design, but one of the aspects, one of the 2 or 3 main ones that makes this quite a good example of good design is the fact that movement has been bumped up the list of priorities, has been made a key feature of the design, and it's exceptionally enjoyable lamp to have. So I'll stop there. Thank you very much once again for your time and your attention. I hope that this short introduction to motion and movement, to human motion movement, has been of some interest to you and hopefully can be useful to you. Very important field. Next week we'll be doing another discussion about human factors in ergonomics as we move through from the physical all the way to the perceptual, cognitive, and emotional. So we're on a journey from the most physical considerations to eventually those emotions we feel. We'll be moving on to the next step in our journey, starting the perceptions on the next week's talk.